In this video, I will cover Rutherford scattering, which is basically an insight into atomic structure. We had discovered the electron with Thomson's experiment and then found out about the charge on the electron by Millikan's oil drop experiment. But now we're trying to find out where are these electrons situated within atoms. In other words, what is the structure of the atom? And it was Rutherford's scattering experiment that famously pointed the way to our current understanding of a nucleus with a then huge amount of empty space before we then see the electrons. So quite a phenomenal model that fits with experiments. So Thomson, who discovered the electron, was working with this kind of assumption for the atomic model, where we have a positively charged atom. And this positive charge is evenly distributed over the atom, and the atom size is maybe 10 to the minus 10 meters or an angstrom. And then the subatomic particles, the electrons, were thought to be embedded within this positively charged atom. And so this was known as the Plum pudding model, because you've kind of got all these electrons kind of embedded within this positively charged background. But it was Rutherford with his scattering experiments done with Geiger and Marsden at the University of Manchester between 1908 and 1913 that they discovered that the atomic structure is actually very different to that, and instead what we have is, for example, what is shown in this video here, where we have a nucleus where all of the positive charge of the atom is contained in this very small core of the nucleus, the core of the atom called the nucleus. And then we have the subatomic particles, the electrons, orbiting around that positively charged nucleus. So this is what he did to come up with that model. This is the Rutherford gold foil scattering experiment. What we have on the left here is a source of alpha particles, and we now know those alpha particles are the nuclei of helium atoms. Obviously, it's 2 protons and 2 neutrons. So we have an alpha particle source. That could be radium, americium, whatever your favorite alpha particle emitter is. And this is in some kind of a shielded lead container, for example. And then we have the alpha particles being emitted from the radioactive source here. This all needs to be in a vacuum, of course, otherwise the alpha particles would be scattered by the air. But within a vacuum, the alpha particles can make their way through into this region where we have a gold foil, which is very thin, maybe 1 to 2 microns in width, in thickness. And when they hit this gold foil, what was expected was that they would just kind of more or less go straight through. But as you can see with this schematic here, we actually get this scattering of the alpha particles. So just like many of the other experiments, we have the usual fluorescent screen there to detect the charged particles after they've scattered. And I think I've now covered all the items in this schematic. So here we are with another look at that experiment. Here is our alpha particle source. You can optionally include an acceleration here to give extra kinetic energy to the alpha particles. So this is a positive and a negatively charged electrode. So the alpha particles are positively charged. They'll be accelerated towards the cathode here. And there's a hole in there so they can actually make it through that electrode and then go into the apparatus that we saw in the previous slide. And then they're going to encounter this thin, maybe 1 to 2 micron thin gold foil and be scattered, and then we're looking to detect them using some kind of fluorescent screen. And of course the point was that Rutherford and his colleagues, Geiger and Marsden, looked for these scattered particles at different angles. Originally they did this with quite a narrow configuration, because they really were not expecting the wide-angle scattering that will be revealed with this experiment. And so they did, of course, specifically design this experiment to look for these wide-angle scatters of the alpha particles. So indeed, just to zoom up again, we've got the alpha particles coming through the gold foil and being detected on the screen just opposite. And then some do indeed get very slightly deviated by the gold foil. But then we begin to see also these rather unusual events where we get quite a large angle of scatter. Now, to put this in context, these alpha particles are very energetic, and the thin gold foil was perceived to be, this is just a super thin layer of just limited number of atoms, and we're basically firing these very energetic particles, and they should just punch straight through, which is what we would see here. But this kind of wide-angle scatter was very much unexpected, even though, of course, they did devise the apparatus to already look at these particular angles. And then this was the real shock result, that there was even complete back scattering of the alpha particles. And so roughly about, say, 1 in 10,000 of these alpha particles would more or less fully backscatter, and so you can have a look almost at 180 degrees to actually see that you get scintillation light, in other words, alpha particles incident on the fluorescent screen even at those very wide angles. And so Ernest Rutherford was very surprised by this, even though, of course, he had devised the apparatus to actually check for it. This is the rather spectacular quote. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and had the 15-inch shell come back and hit you." So that was his reflection on this experiment. And as we know now, of course, he got the Nobel Prize in 1908 for investigations into the disintegration of the elements and the chemistry of radioactive substances. So this schematic shows what the Thompson model was like, with the positively charged background and the electrons kind of embedded within the atom, and the expectation being that these alpha particles, shown by the black rays here, black arrows, would just pass straight through. With the Rutherford model, this is how we can explain that backscattering of the alpha particles. Obviously, most of them can still pass through, but then if we have this very dense core of the atom, the nucleus, right in the middle here, then when an alpha particle is approaching this, it will be deflected backwards. This is going to be a positively charged nucleus holding the entirety of the positive charge of the atom. And so there's going to be a serious electrostatic repulsive effect here on the positively charged alpha particle, which itself is a nucleus of a helium atom, approaching the nucleus of a gold atom, which has far greater positive charge. And so that explains the gold foil scattering results, shown again here, where we've got these kind of wide angle scatters compared to the expected outcome with the more or less shooting straight through of the alpha particles, which didn't happen. The observed result is the one on the right hand side, best explained by having a nucleus in the middle of the atom. So let's take a look a little bit at the mathematics here, and to try and figure out what is the size of the nucleus relative to the atom. We know that we're getting these very severe backscatters, but what can we figure out about the size of the nucleus? So what we're going to do here is assume a head-on trajectory of the alpha particle heading towards a nucleus of a gold atom. This is one of the atoms in that gold foil. And then what we're going to say is that there's a kinetic energy of these alpha particles given by the classic half mv squared. We'll just call that capital T to denote the kinetic energy. We know that the alpha particle has a charge of 2 times E, where E is the charge of an electron. So this is 2 protons and 2 neutrons, and so each proton has the same charge as an electron, but the positive rather than the negative charge. So therefore, this is a charged particle with charge 2 E, or Z1e. This is going to be approaching this gold nucleus. For the gold nucleus, we have an atomic number, where the atomic number, of course, tells us how many protons there are in the nucleus. So it's an atomic number of 79 for gold. That means the charge of a gold atom, in particular a gold nucleus, is going to be 79 times E, where again E is the charge, the fundamental unit of charge. So, applying our knowledge of electrostatics, we can find the potential energy of a helium atom when placed within the vicinity or proximity of a gold nucleus. And so the potential energy, when you've got two charges close to each other, so it's like Q1, Q2, the potential energy is just Q1, Q2 divided by 4 pi epsilon naught times the distance between the charges. That's just a standard definition of electrostatics. So what we're going to do then is just equate the kinetic energy to the potential energy. In other words, the kinetic energy of this incoming alpha particle is going to be reduced because effectively it's being converted to potential energy as it gets closer and closer until it finally stops at a limit as it approaches that gold nucleus. Of course, if this kinetic energy had been even greater, then it would get closer and closer, and in fact in some experiments you can even actually go into the nucleus. But here we're nowhere near that energy range, and so we're getting close to the nucleus and then bouncing backwards. And so what we can do is look at that distance of closest approach just by equating the kinetic energy of the alpha particle with the potential energy between the alpha particle and the gold nucleus. In other words, what is the position needed where basically the original kinetic energy of that corresponds to a potential energy within the vicinity of that gold nucleus. And so just by using the standard equation for potential energy, equating it with this, we can rearrange it and find that therefore that distance d of closest approach is just z1, z2, e squared over 4 pi epsilon naught t, where again capital T is the kinetic energy and epsilon 0 is the permittivity of free space. So if we plug those numbers in, and to do that, we're going to have to assume an alpha particle kinetic energy. And so we're going to use 4.87 MeV, which is a very reasonable choice of kinetic energy for an incoming alpha particle in this kind of experiment. And then we're going to plug in that value of T for the kinetic energy into that expression we just looked at. Plug in the value for Z1, which is 2 for a helium nucleus for the alpha particle. It's 79 for Z2, that's the atomic number of the gold nucleus. And of course we've got E here, the charge, fundamental unit of charge, multiplied by 1 over 4 pi epsilon naught, so that's this expression here, can be called the Coulomb constant, divided by that kinetic energy as shown here. So we've got to convert the 4.87 MeV, we've got to put that into joules for this expression to hold, and so that's why we're doing the capital M is a million, so that's 10 to the 6 times an electron volt in terms of 1.602 times 10 to the minus 19 joules. So this expression here is in joules. And if you solve that, you'll get a distance of closest approach of the helium nucleus, the alpha particle, to the gold nucleus, a value of about 46 times 10 to the minus 15, suggesting therefore that the size of the nucleus is within this approximate range, 10 to the minus 14 towards 10 to the minus 15 meters. And we know already that the size of an atom is about an angstrom, 10 to the minus 10 meters. And so therefore that's why we can see that there's at least this kind of scale factor between the nucleus and the atom. There's about a factor of 10 to the minus 4 there. So in other words, the nucleus is only 10 to the minus 4 the size of the overall atom. So if you like, it takes up roughly 1 part in 10,000. If we were to divide the diameter of the atom into 10,000 parts, we could say that the nucleus occupies about roughly 1 part in 10,000. So this is the situation we've just looked at. There's the helium nucleus, showing it with 2 protons, 2 neutrons, and there's the gold nucleus, just to give you a visualization that the nucleus, therefore, is this tightly packed, densely concentrated positive charge. Now, to take a look at that scale that we've just considered, we'll look at the case of a hydrogen atom, where we're going to consider a single proton as the hydrogen nucleus, and then we're going to look at the distance of an electron from the hydrogen nucleus. And this is called the Bohr radius. We'll get on to the Bohr model of the atom in later videos. But for now, let's just take this Bohr radius to be about 0.5 times 10 to the minus 10, exactly what we would expect, because an angstrom, about the size of an atom, is 10 to the minus 10. And so, of course, the radius of an atom, if you like, is about half an angstrom, and that's what the Bohr radius is, although this is elegantly calculated via the Bohr model of the atom, a beautiful model which we'll get into later. So let's take a look just to try and comprehend this. I've done a rather, maybe you can do your own comparison. This is the one I chose. I compared the size of a nucleus to the size of my laptop that I'm recording this video on, so about 30 centimeters, just if we take one dimension of the laptop. And then if you do the ratio, so here I'm looking at an atomic nucleus of size 1.6 up to about 15 times 10 to the minus 15. So I'm not sure which value I chose, but something around about 10 to the minus 15. And I did that nucleus size compared to the Bohr radius, and you end up with this rather phenomenal outcome. So it's as if the nucleus is the size of my laptop, and the electron orbiting it is about 8 kilometers away from my laptop. So that is really quite mind-blowing if you think about all the empty space between a laptop and a point about 8 kilometers away. Quite a phenomenal thought to have in terms of what an atom is. You know, lots of empty space, basically. Also, you could do the mass comparison between the nucleus and an electron. So again, the hydrogen nucleus, if I take that as the mass of my laptop, say about 2 kilograms, then the electron is about the weight of a sugar cube. So you've got a laptop and then you've got a sugar cube off at 8 kilometers away from my laptop. So awful lot of free space in an atom. Okay, so where we're going to go next is we're going to have to go further in our understanding of the atom and to get into the Bohr model of the atom. We're going to have to get into a bit of quantum physics now. And a key step in quantum physics was what Albert Einstein put forward based on prior work from Planck, who worked on emission spectra. And so that means in the next video we've got to cover the photoelectric effect, which was a previously or rather classically unexplained phenomenon. Classical physics just didn't explain the photoelectric effect. We have to get into the quantum world to understand the photoelectric effect, and so that's going to be our next stepping stone, because we need that to understand atomic structure at the next level. So meanwhile, thanks for listening.